We're ready to go. Good to see you guys, and hi Clara, sorry that we're missing you. We are recording today's lecture because Clara figured that she might be absent and asked us to do that. We've got several things on the agenda. The first thing that I'm going to take a look at are homework questions, and in particular, we're going to take a look at page 67, numbers 44, 51, 53, all of which ask us to read limits based upon limits from left and right. And then after that, we're going to take a look at some examples of using our special limits. And to do that, we need to first review the material from yesterday. When we get to examples of special limits, I have an announcement about the homework and correction that needed to happen to one of the problems. So there it is. So let's begin with the homework questions, page 67, numbers 44, 51, and 53. I have again. I have number 44 right here, and the questions that are asked are: what is the limit as x goes to 2 from the left of g of x to the right, and what is the limit as x goes to 2 of g of x, and finally, what is g of 2? If we're looking at the limit as x goes to 2 from the left, we are talking about the value that g of x approaches for x close to but less than 2. So we're talking about x values that are just to the left of 2 here. We are going to exclude from consideration all of this nonsense over here and all of this nonsense over here. The only thing that matters are the g values right in the neighborhood of 2 and to the left of 2. And when I look at those values seem to me to be very close to what number? 1. So this limit from the left is 1. Now we come back and ask, what is the limit from the right? And when we ask about the limit from the right, we are considering values of x that are in the neighborhood of 2 and to the right of 2. So these values here. We're going to exclude from consideration all of this over here. We don't care about anything except x's that are close to and slightly greater than 2. And when we do, it looks like my f of x values are going to what value? 1. Now we are asked about the limit as x goes to 2 of g of x, and we have all the information that we need because of our two-sided theorem. Since the limit from the left is 2, and the limit from the right is, from the limit from the left is 1, thank you. The limit from the right is 1, therefore the limit as x goes to 2 is 1 in the story. But wait, what about this dot? Doesn't matter. The limits from left and right are both 1. The overall limit is definitely 1 also. Now what about g of 2? G of 2 is the value that g has when x is actually equal to 2. And when we ask that question, there is one and only one x value that we care about. And that x value is right at x equals 2. And the value of g of 2 is 3. Yes?
We use opposite side of here. We can use
If you can find bounding functions. But I think you wanted the two-sided theorem because we've got the condition then right there. Okay, yep. Good. Any other questions? All right, let's take a look at number 51. In number 51, we are given a piecewise function, and we are asked to evaluate the limits from the left and right as x goes to 2. So I'm going to write, I'll do the limit from the left over here. The limit from the left can be written, limit as x goes to 2 from the left of 3 minus x. And the reason that I'm using the 3 minus x here is that that is the piece for which x's are less than 2. And so as x goes to 2 from the left, 3 minus x is going to go to what value? 1. And there it is. For the limit to the right, same story, but I need to use the piece where x is greater than 2. So that piece is going to be x over 2 plus 1. And as x goes to 2, I get 2 root 2. So the limit from the right is 2. What about the limit as x goes to 2 of f of x? I can immediately appeal to the two-sided theorem. Limit from the left is 1, limit from the right is 2, limit overall does not exist because the two values are different. What about, they don't ask this question, but what is f of 2? Does not exist also. Right, good. Because there is no specification for f when an x is equal to 2. It's not in the domain of the function. How are we doing? Okay. Now here, in number 53, they ask a slightly more sophisticated question. We'll tackle this question here. The limit as x goes to 1 from the left of f of x, meaning the limit as x goes to 1 from the left of 1 over x minus 1. What do you notice about the form of this limit? If the form is 1 over 0, and that is a sign of trouble. We will know more precisely how to deal with that in coming days, but for now, we take a look at the graph of 1 over x minus 1, and we see right at x equals 1, there is a vertical asymptote. Like that. And this indicates that no matter what value I might pick, 1 over x minus 1 will get smaller than that value for x's that are close enough to 1. And this means that my limit does not exist. Some of you on your homework also put negative infinity, and that's an appropriate answer as well. What about from the right? From the right is a lot tamer, because I'm now taking the limit as x goes to 1 from the right of what?
X cubed minus 2.
X cubed minus 2x plus 5. And that's a simple polynomial substitution. I get 4. And there it is. What is the overall limit? It does not exist. The limit as x goes to 1 of f of x does not exist. What about f of 1? Well, it's 4. Because when x is 1, f of 1 is 1 cubed minus 2 times 1 plus 5. Yes? Uh-huh. Let's take a look. First question, did you remember parentheses? That's the big issue for students. That fraction bar is a grouping symbol, and you have to make sure that you group. So here comes 1 over x minus 1. You have something different? Let's take a look. This is, okay. See if you can see what happened with Jason here. This is what Jason's looks like. Really hard to figure out. Yeah. This is a thing that the Texas Instruments calculators do, and the whole math world hates them for it. Sorry, guys. And that is that for some reason they decided to have two different signs. One of them was a unitary negative sign, and the other was a legit subtraction sign. And if you enter this as 1 over x negative 1, the calculator will interpret this as 1 over x times negative 1. And when you graph, look, my graph looks different. It has a vertical asymptote at 0 because it is the graph of negative 1 over x. And there it is. So all that happened here was you confused the unitary negative sign for subtraction. And once we fix that, there it is. In my mind, there's just no justification for that, for them to have done that. There it is. We've got to live with the calculator that we have. Any other questions? Okay, fantastic. Let us now review the material that we covered yesterday. Remember that it came in 3 pieces. The first piece was 2 special limits that everybody needs to know. The limit as x goes to 0 of sine x over x, and the limit as x goes to 0 of 1 minus cosine x over x. What are the values of these limits, everybody, all together? Top one is 1, bottom one is 0. Good. You need to know these. And the reason for that is that we're actually going to use them in the month of October. Fancy that. Learning math that we're going to use. The second thing related to this is the proof of the fact that the limit as x goes to 0 of 1 minus cosine x over x is in fact equal to 0. And everybody needs to know how to do this proof as well. Do you remember roughly how it goes? Rationalize, right? And after we rationalize, then we use our product rule to peel off the factors of sine x over x and everything else. Yep. So everybody needs to know how to do this also. But then, as bonus material, we have the limit as x goes to 0 of sine x over x, proof of that fact. And the essence of that proof is that first we construct our unit circle, and we observe that the area of the inside triangle is going to be less than or equal to the area of the sector, which is going to be less than or equal to the area of the outside triangle. We apply the sandwich theorem. So that's not so bad either. But at this level, that would be like a bonus quiz question. Okay. Yes, sir.
Where?
Does your assignment sheet say so? Check.
It's like Thursday or quiz on?
Yeah, so here's how to read that. If you take a look at Edmodo, Kerchink, and you look at the assignment sheet, where it says quiz on limit techniques, that means that there's a quiz on limit techniques.
On Thursday or?
On Thursday, correct. Yeah, so this is everything that you do on this day. You have a quiz, you read this, you do this on
What's limit?
Ah, good question. So for your quiz, we're talking about For the limit techniques, we're talking about the following. First of all, evaluate or estimate from graphs, including graphing calculator. We're talking about limit properties. And the limit properties gave us a technique of direct substitution for certain types of functions. Which types of functions? Polynomials, rational functions, yep. And although we haven't fully gotten there yet, I have given out a sneak teaser. In general, it's going to be any continuous function. And then in addition to the limit properties, we also had the alias theorem that led to a couple of techniques of cancellation and rationalization. And finally, we had the sandwich theorem. And the sandwich theorem was our tool for finding two special limits that we just talked about. So in some sense, this is all of the material that we have covered here concerning limits. And yet it's not so bad, right? Because you guys have been doing all of this and you've been doing it fairly well. Yes?
What is estimate from graphs?
Estimate from graphs. So when we did this limit right here, we were estimating from a graph. Okay? No? Not okay? Yes, okay. Okay. Good. All right. Well, what I thought I would do is go over a couple of examples of using our two special limits that will look somewhat similar to the ones that are in the homework. I do need to make an announcement about your homework, so coming back to where we are, done a review, homework questions. We're going to do some examples of special limits, but before I do that, on your special limits homework, the question number 2, a typo snuck in there that made the problem harder than it needed to be. I've put in an updated version on Edmodo, so if you pull it up now, it has the right problem. But the problem it has stated was the limit as x goes to 0 of x cosine x minus x squared all over x. And this limit turns out to be a pain in the neck, because if I try to simplify it by, say, factoring, I think this was over x squared here. Yeah, as x goes to 0. If I try to simplify it by factoring, then I end up with something that looks suspiciously like a special limit, but it's different in one term, right there. This is not the question that I intended to ask. The question that I intended to ask is much simpler, which is the limit as x goes to 0 of x cosine x minus x all over x squared. And this one you can handle with a little bit of algebra. Okay?
I did use the first one.
You can get somewhere with the first one. When you do, what you end up with is infinity, or limit does not exist.
From -1.
Because when I cancel this common factor, I get the limit as x goes to 0 of cosine x minus x over x, right?
I can do it this way. So I wrote as limit x goes to 0, x cosine x over x squared minus 1.
Okay? We can still do that from here. Break up the fraction, like so. But now this limit right here fails to exist. Check its form. The form is 1 over 0. other
Like
side.
form 0, 0, you can use that sometimes without.
Yes, but my form here is not. My form is 1 over 0. We'll actually discuss this form later on and call it the infinite form. But for now, suffice it to say that if I end up with something like this, my limit fails to exist.
Is there any difference between 1 over 0 and 0 over 0?
Yes, very much so. A form of 0 over 0 which I have called the indeterminate form. Is a form that indicates to me that I still have some work to do to determine what form, what number the limit actually is. Okay? So the limit might exist, might not, and it could be any number. I don't know yet. I have to do some work. Usually that work is algebraic, finding a common factor. So very, very, very often, this is indicating that there is a common factor. And in fact, at a very deep level, this is actually always true if you think of, if you represent functions as integers. By contrast, we have not gotten here yet. I'm just answering your question. This form right here is going to indicate that my limit does not exist every single time.
Always.
Always. And the reason for that is really simple. I'm taking some number that is very close to 1 or any other value and dividing it by very small numbers, and we get a very large result. And
Can we put that 15?
yeah, you can, but we'll have to deal with sign, plus or minus infinity later on. Yeah. So for now, just say it does not exist. Does that help? Okay. All right, here are a couple of example problems that I want to pull out there. Let's take a look at the limit as x goes to 0 of sine squared x over x. And when we look at this, it looks very, very, very similar to one of our special limits, right? How is it different?
Sine squared.
Yeah. Can you think of any way to extract our special limit from this? Okay, go ahead.
There's x goes to 0, sine x over x. Minus x goes to 0.
What does sine squared x mean? Means sine x times x. Sine squared x is just a convenient way of writing sin x squared. And so that means sin x times the sine. All right, go ahead. Now that we've extracted sin x over x,
That's 1.
yep. And I often use these large arrows here. This whole limit goes to 1. What does this go to?
Sine 0
Sine of 0, but sine of 0 is not 1.
is
0.
0, yeah. And we're done.
It's the first question.
Now let's do a little bit of reconnoitering here. How exactly, what was the successful strategy for making this limit work out?
You need to try to make it to the special limit.
Yeah, I needed to basically try to find the form of my special limit. spirit here, somewhat like a scavenger hunt. I'm going to try to find the form of my special limit somehow. Yes, sir.
Or how do you know that that's a special limit or not?
How do I know what?
That's a special limit or not?
How do I know if it's a special limit or not? Well, I only have two. And here they are.
Okay, like random question.
Right. So I give you a random question, you think, I wonder if any of my special limits are counted. It's a thing to think. Why not? Let me give you another one. See what you can do with this. Good job.
One.
Yeah.
Tell me how.
One.
Separate.
How do?
Tell me what to write.
Sin X over X.
Limit square.
Ah, yeah. But give me the whole thing,
Oh, okay.
not part of it.
X to
X goes 0. Limit x goes 0 sin x over x times limit x goes 0 sin x over x.
Mhm. We can either think of this in terms of power rule, or we can think of it in terms of product rule. Both are valid. The language here is limit as x goes to 0.
Limit as x goes to 0.
Your turn.
limit X X.
And you go.
Oh, limit as x. Limit x.
Limit as.
As x goes to zero.
There it is. Good. Good. Okay. And so now we can observe that our special limit is right there. We get 1 squared, which is 1. We're done. See, we found the special limit. I'll try this one. This one's going to be a little bit more clever. There's an example like this in your homework. I put in a couple of example problems here. Here, this greatly resembles my special limit. But it is not exactly in the form of my special limit. One thought that I could have is maybe I've got an identity for sine 5x. And my second thought is maybe I don't. But a common theme in mathematics is perhaps a clever substitution can substitute my troubles away. Perhaps a clever substitution. And in particular, I observe that the problem spot for me is right there at 5x. I've got this sine of 5x thing and I don't know what to do with it. So, I'm going to try letting y equal 5x. I picked the variable y out of the hat. I could have chosen u or theta or anything. I'm going to try let y equal 5x. And now the spirit of substitution is that I'm going to walk through and replace everything here in terms of y, so that I can now evaluate the limit in terms of y. Maybe it'll help, maybe it won't, but it's not too hard to try. Since I am letting y equal 5x, sine of 5x is the same as sine of. But here's where you have to be careful. If y is 5x, then x is the same as. Yeah. And then finally, this is the part that students will sometimes have difficulty with. If x is going to 0, what is y going to? Hint.
0.
Yeah. What is the limit if x goes to 0 at 5x? So if x is going to 0, y is going to 0 also. So what I have done now is to replace a limit that was hard for me with a limit that might be easier for me. And in fact, I think it is because I think I see my special limit. almost. Can I rewrite this with a little bit of algebra? I think I can. Division is multiplying by the reciprocal. And so I can rewrite this as sine of y times 5 over y, or even better. The limit as y goes to 0 times 5, times the limit as y goes to 0 sine y over y. This is product rule. I could easily have used a constant multiple rule as well. But either way, I get 5 times 1, which is 5, exactly as you predicted, Jennifer. Does that make sense? Now, here's where this gets really interesting. She thinks should be 2. Prove it.
So I need to change it to sine 2x over 2x.
Ooh. How about 2x over sine x? Has to be. Because what we're doing here, very, very clever strategy, not the only one we could have taken here, but the clever strategy is to multiply by 1. Specifically, she ends up multiplying by 2x over 2x. And she peels off one factor here, and peels off one factor here. Now, what inspired you to do that?
It looks like I should do that.
Okay, it just came to her intuitively. Great. That's one of those things where the first time you see it, it's a brilliant idea. The next time you see it, you go, and the third time you see it, you go, wow, that's a technique I need to remember. So multiplying by 1 is a real thing. And we've seen it in the context of fractions, right? Now here we're seeing it in the context of fractions that give us special limits. Okay, keep going, Jennifer. You're doing well. I need some more detail.
Okay, so let's then substitute 2x with y.
Okay.
And sine y over y.
What about over here?
You, like, what I just said is I try to move to, like, outside.
I'm sorry.
It's like 1 times 2.
Yeah. There we go. Now, this was fairly sophisticated. So let's see what we did here. First of all, we have a little bit of product rule for our limits. That allows us to split the factors. So there goes our product rule. But also, what rule for limits allows you to pull that constant to the outside? What's it called? Oh no, these limit properties have names. And I know that you can execute them, but you want to know their names also. Product rule is one way to think of it. Constant multiple rule is the way that we yeah. So this is our constant multiple rule, or CMR, which says that the limit as x goes to c, k times f of x is the same as k times the limit as x goes to c. And now that we have this, we have, hey, our special limit. We we have the reciprocal of our special limit. So its value should be 1 over 1. And so we end up with 1 times 2 times 1, or 2, as the final value. Now, I said that there was more than one approach here. Did anybody have a different way of getting to this limit? Other than multiplying by 1 and being clever?
Might be the substitution.
Possibly. But if you try substituting directly, then you end up creating problems for yourself. Question. Focus just on the sine 2x right here. Do you know anything that sine 2x is equal to?
I like doing the trigonometry identity.
Getting what?
2 x minus 1.
Sine
2
2.
sin x equals cosine x.
That's it. We can pull out our double angle identity for sine 2x and replace sine 2x with what it is, which is 2 sine x cosine x. And lo and behold, we do that. Yay! And now as x goes to 0, cosine x goes to 1 times 2, which is 2. I like that actually a little better, but it was specific to sine 2x. And so it's not as general. It relied upon an identity, but it sure is cute, isn't it? Okay, well, these are the examples that I wanted to go through. Question?
Are ones like this discriminant ways or not for a second?
Could be. Fair game. You've got another one like it in your homework. Yep. Okay, well, I will see you guys tomorrow. Take care.